Well, in that case, we'll start off with our warm-up problem. Might take us a little bit of time since there's a bunch of options here. Determine if the following are true or false. So we have a bunch of statements. And so if you recall last time, we were talking about properties of numbers. And, well, numbers are really important to mathematics. Mathematicians like numbers, and in some sense, they're important to life. You know, you have to understand things quantitatively. You know, that helps you really understand what's going on. Now, before we start going through this, I want to make sure we understand what we mean when we say true. So, let's start with true. When we say true, what do we mean by true? Do we mean it's sometimes true, it's usually true, it can possibly be true, or it's always true? Always. So when we're saying something is true, it always has to work. So in other words, if you make a general statement, say involving letters and symbols, if you substitute in something for those symbols, some set of numbers, it's going to work. Now, what does false mean? Philosophical question. What does it mean to be false?
It doesn't always work?
Yeah, it doesn't always work. It may never work. So false is just not true. So if it fails in even one case, it's not true. And it's false. If it fails in all the cases, it's definitely false. So you can't prove something is true with an example. All you've shown is that it works in that case. But you can prove something is false with an example. All right. With that in mind, let's go through these. A. You're adding two fractions, a over b plus c over d, and the result is a plus c over b plus d. Is that true or false? False. False. Okay, good. You can't add fractions this way. Now, again, there are cases you can concoct where it's true, but it's not always true. You can just make up, in this case, it's not hard to come up with examples. If you have a half plus a half, that doesn't equal 2/4, because 2/4 would be a half again. Okay. So B. Here you have x times 2x plus y times 2x plus y, and it claims this is x plus y times 2x plus y. True or false? True. Good. What's being demonstrated here? What property? Do you recognize it? Yeah, you're basically doing distribution. You're multiplying that 2x plus y through. And you can think of, this is sort of one notion, you know, this plus sign, plus can do two things. It can separate things and say, think about these as two different parts, and also unite things. So really, you can think of this 2x plus y as just a blah. X times blah plus y times blah. And then you're factoring out the common blah. Well, that's factoring is something we'll get to in a future discussion. But distribution. All right. A times b minus c is ab minus c. True or false? False. False. All right. Be careful. This comes, again, back to distribution. You have to put that a times c there. All right, so be careful. All right, D. A divided by B, and so this symbol here, in case you're trying to figure out, that's the divide symbol. A divided by B, take that, divide by C. That's the same as 1 divided by C, all divided by B divided by A. True?
Yes.
Okay. Now, when in doubt, just think about what it means. What's another way to think of A divided by B? A over B. Because when we talk about dividing, you can think about it as multiplying by the reciprocal. So if I want to divide by B, multiply by 1 over B. So it becomes A over B. If I want to divide this by C, I can achieve that by multiplication. What do I multiply by? 1 over C. So this becomes A over B times C. What's the way to write 1 divided by C? 1 over C. Now, B divided by A, that would be B over A. If I want to divide by B over A, what do? Multiply by the reciprocal. Great! So then I have upstairs 1 times A, which is A. Downstairs I have C times B. That's the same as B times C. That's our commutative property. Both of these are equal to the same quantity. So this is going to be true. Now, I should have probably thrown in assume that these are all non-zero, but we're amongst friends. So we know that. We would never divide by 0. Never, never. All right, last one. Okay, so here we have a product. U minus 3 times 2u minus 5, and we're told it equals 1. Then our conclusion is, well, either u minus 3 equals 1, or 2u minus 5 equals 1. True or false? It feels familiar, right? People have said false. Okay. Why? Do they both have to be 1? So maybe the problem is this or. I mean, if these are both 1, then certainly 1 times 1 equals 1. Is that our problem? Yeah, so someone noted, haha, the real thing is like the principle, the philosophy is we don't really want these things to be 1. We really learned that, hey, if this is 0, this is true. So what happens is 0 has this really awesome property that the only way you can multiply things together and get 0 is if one of your terms were 0 to begin with. No other number has that property. Is there a way to multiply two things together and get 1? Anyone have a pair of numbers that does that? Which are not 1. Sorry, what? -1 and -1 does it. Any others? 1/2 and 2 does it. 1/3 and 3 does it. There's many, many ways that you can multiply things together and get 1 where these terms don't have to be 1. It's 0 that has that property. And so this is a false statement. All right. Good. Good. Well, that's our review. Now, what's going on? Well, I like to sort of have a thought for the day. And today, I just want to talk for a second. This is more psychology, but be aware of and work to overcome learned helplessness. Now, what's learned helplessness? What can happen is that you may have experienced in the past challenges. And in other words, you've had a bad experience with math, but it can actually be, in some cases, I have to be careful how I say this. You might have thought you were bad at math because you struggled. And it can start to reinforce in your mind. I struggled with math, I must be bad at math, and then that causes you to struggle more with math, and it makes you bad at math. Now, this is a very simplistic way of saying learn helplessness. Experiences form what you think you can and cannot do. Don't let your past dictate what you're capable of. You can learn this material. This course is set up to help you succeed. You can succeed. Don't listen to that inner dialogue that might say, you're too much and not enough, or you can't do it. You can do this. You can do this. Persist. Continue to work on these ideas, these topics, these problems. You can succeed. Now, what we're talking about today, our goals for today, we're going to be working on polynomials. And we're just going to say, what are polynomials? And work to simplify expressions. We're going to keep talking about polynomials for a while because, well, quite frankly, we love polynomials. And we'll get into that. All right. So, to start, before we do the formal definition of polynomial, we have to talk about writing things with exponents. So when we talk about exponents, we have something to powers. So something to a power. We'll say b to the n. And I'm using b here just to emphasize b for base. So that's what's downstairs. Upstairs is n. That's the exponent. Probably not the best choice. We don't want to use x because that'll make it confusing for what follows. And unfortunately, nexponent is not a word, but oh well, such is life. For now, we're going to work where our exponents are whole numbers. They do not have to be, but that's where we begin. We will talk about more general types of exponents next week. So, when we talk about b to the power n, what does that mean? It means we have lots of b's. b times b times b times b, b, n times. So n copies of b multiplied together. And we can do something very simple. If I have b to the n, b to the m, same base, so the b's downstairs match, then upstairs I have n and m. Well, it just says I have a bunch of b's, I have another bunch of b's, and then I say, well, I have n b's in the first, m in the second. All together that makes n plus m. So that says I have b to the n plus m. So we add the exponents. So b to the n times b to the m, add what's upstairs. Don't multiply, add. Now, one note here. This is a place where people can make mistakes. And so I just want to draw attention. When we have exponents, exponents only attach to the thing right above it, right where it's above. So, when we have 2 times t to the fourth, what we mean by that is that's the number 2 times t to the fourth. It does not mean you take 2t raised to the fourth power. Another one where people make mistakes is where there's a minus sign. So if you have minus 3 to the 6th power, that means take negative 1 times 3 to the 6th. It does not mean take negative 3 and raise it to the 6th power. And this is an important distinction. What's the difference between these two options listed here at the bottom? Yeah, the sign. We saw the sign, and it opened up our eyes. We saw the sign. One of them will end up being a negative number. One of them will end up being a positive number. Negative 729 versus positive 729. And negatives and positives are different. You want to keep track. All right, now we know how we think about these exponents. So we can form what I like to call monomials. Mono, meaning one term. Poly will mean many terms. What does a monomial look like? It can be something as simple as a number, or maybe a number times some variable raised to an exponent, or maybe a number times a variable raised to an exponent times another variable raised to an exponent, so forth and so on. So there's no addition. It's all a product. It's a product of a number. And by the way, when we talk about a number here, these have another name. We call these our coefficients. So if you hear the word coefficient, that's that number in front. So there's a number and possibly variables raised to powers. There can be more than one variable. There can be as many variables as we want. I think we'll usually limit ourselves to 1 or 2. So what are examples? 5, that's a number. 6y, that's a number times a variable. Now notice here, when we write down 6y, there's sort of an implied number. What's up here if we don't write something down?
1.
Yeah, 1. So there's always that sort of implied number going on. There's a 7, u squared, w fifth. In this case, we think of our u and w as representing our variable terms, and so forth and so on. There's many, many possibilities. All right, so finally, once we have a monomial, we can do a polynomial, and the idea is add a bunch of these terms together. And that's it. So we can have all sorts of things. 8 plus 5x squared, that's a polynomial. 0, perfectly fine. 3x cubed plus the square root of ex plus 7. You might say, whoa, what about the square root of e? Well, what about square root of e? What is square root of e? It's a number. It's a weird looking number, and maybe we're not comfortable with it yet, but it's a number. And so any kind of number works. It can be a fraction, a whole number, it can be an irrational number. We're not putting any restrictions. The only restriction we're putting ourselves on is that the exponents have to be whole numbers. And when there's no exponent, we just assume that means a 1. So these are examples of polynomials. These are non-examples of polynomials. So x squared plus 3 plus x to the negative 4, what's wrong with this one? What's wrong with x squared plus 3 plus x to the negative 4? Why is it not a polynomial? Yeah. We want our exponents to be positive whole numbers. And I apologize if I didn't make that explicit earlier. Positive whole numbers. What about x plus 2y over x plus y squared? What's wrong with that? Like almost everything, right? What's this doing downstairs? We're not supposed to have stuff downstairs. That's a variable stuff. Not going to work. Wouldn't be prudent. So this is an example of what's called a rational function, something, again, we'll talk about in the near future. How about square root of x squared plus y squared? What's going on with that one? Now, in case you're not familiar with the square root, what's another way you can write square root of something? Square root can be the same as to the 1/2 power. And now, what's our problem? The 1/2. Now, quick check. If I have x plus 2y plus 3 cubed, is this a polynomial? Not so clear, but what do you think? I mean, there's no penalty for a guess. And I'm not claiming that it's obvious from what we've written down. What's your feeling? Do you think this is a polynomial? Do you think this is not a polynomial? Okay, so some people have said yes. It is a polynomial because you can rewrite it, but we haven't learned how to rewrite it. So it's not so much that the power being there is the problem. The problem is that it's a 1/2 power. Because it's a 1/2 power, there's no way to write it as a sum of monomials. Whereas this, with some work, you can. Now, why do we love polynomials? I do want to make a comment before we leave this slide. Why do we love polynomials? Because if you look in math, we definitely have a love for polynomials. And if you talk to any friends who might be taking the Calculus 2 course at the end of the semester, besides them looking frazzled, what will they do? They're going to spend half their semester in that class saying everything's polynomial. We love polynomials. And why do we love polynomials? Well, it all boils down to polynomials are based off of the two things we like to do. They're based off of adding things together, and they're based off of multiplying things together. So you can add and you can multiply. That's why we love them. And you might not think that's that much that we can do, but there's these wonderful devices that people love called computers. What can computers do? They can add and they can multiply. And that's it. And you hear about all these fancy chips. There's like NVIDIA. They make a lot of money. What do they make? They basically make chips that add and multiply. That's it. That's their business model. Here's something that can add and multiply a lot of things really quickly. So we can get a lot of mileage out of addition and multiplication. And that's why we love polynomials. Okay, so a few more things to talk about. We have the degree of a polynomial. Now, it's easier to start with monomials and say, okay, what's the degree of a monomial? So monomial, we say, don't worry about the coefficient. Look at the variables. And look at the exponents of the variables. And add them together. So I have a bunch of variables. Maybe I only have one variable. But if I have multiple variables, I add their exponents all up. And that's the degree. Now, what if there are no variables? In other words, maybe it's just a constant number. Well, in that case, there's two cases. If my constant is not 0, we say the degree is 0. And in some sense, that makes sense. You can say, well, that means that all the variables are there to the 0th power. By convention, we like to think of something to the 0th power as 1. If I add up a bunch of zeros, I get 0. If the constant is 0, so if I see the term 0, the textbook says it's undefined. Other textbooks will say the degree is minus infinity. That's a fun discussion to have. But we'll go with the textbook and say it's undefined. And that might seem strange, but there's a reason for that. All right. So let's talk about our degrees. Here we have 4 options, and the question is, how do we find the degrees? Oh, I talked about the degree of one monomial. How do you find the degree of a polynomial? The answer is you look over all the monomial terms and say, which one's the largest? So you take the max of all the monomial terms. All right, so here we go. Find the degree of the following. So I have here, these are all polynomials. They use different symbols. The variable names can be whatever we want them to be. That's the nice thing about math. We have flexibility. For the first one, that's a monomial. What's our degree of that monomial? 3. So what's the overall degree? 3. right? Because you just take the largest one, there's only one. What are our degrees? What's the degree of this polynomial? 5. And if you went through the individually, what would our respective degrees be? 2, 0, because there's no x. So if it's a constant, that's degree 0, and 5. Largest, 5. Okay. How about C? What's the degree of the polynomial? I heard a 2. Is that right? Well, let's look at our degrees. What's the degree of the first term? If I see v, I think of it as v to the 1. So what's the sum? 3. All right. How about this term? 3. And here? 2. And here? 0. Those are the degrees individually. Now, I have a tie. Oh my gosh, how do I break the tie? Do I need to worry about that? No. What's the largest number? 3. Okay, last one. What's the biggest degree here? What's the degree of the polynomial, if you will? 12? Okay, let's check it. First term, what's the degree of this monomial? 7. And here? 8. And in here? 12, right? Because there's a 1 implied. 1 plus 9 plus 2 makes 12. And the largest of these is 12. All right. Good. So, now we want to work on combining polynomials. So that, of course, we like to do two things. We like to add, and we like to multiply. So, let's talk about adding. When we have two or more monomials that have their variables to the same powers, and in other words, I look at the variable parts and those match, I can combine them together into a single one by adding the coefficients in front. All right. So, for instance, here we have 3x squared plus 5x minus x squared plus 7 plus 6x plus 2 minus 3x. So I like to work through it by thinking about my terms in terms of my powers. Now, everything here has powers of x's. And I like to start with my highest power. What's my highest power? The power 2, r to the square. And so I say, okay, what things have an x squared? I see two things with an x squared. So if we combine them together, what do we get? 2x squared. We just add the coefficients. All right. Then I go to the next power down. Next highest power is x. How many x terms do I see? There's 3 of them. 5x, 6x, and that minus 3x. If we combine all of those together, what do we get? 5 plus 6 and minus 3. That is indeed 8x. And finally, we get our constant terms. And we have two constants, plus 7, plus 2. Always pay attention to these pluses and minuses. Pluses and minuses matter. Put those together. 7 plus 2 gives us 9. So that reduces to 2x squared plus 8x plus 9. X squared plus 3x becomes x squared plus 3x. Ha ha ha, trick question. Okay. You can't combine these. Why can't we combine things here? These exponents don't match. It's, apples and other types of apples, right? These are not compatible with each other. So you can't put them together. All right, so that's adding. So you add monomials as long as the variable part matches. To multiply, you probably are familiar with the word FOIL. This is taught a lot. FOIL stands for first, outer, inner, last. And the idea is we're taking two polynomials, we're going to multiply them together. And so in FOIL, what do? You take the first terms, that gives you your x squared, your outer terms, so that's your x and minus 1, that's your minus x, your inner terms, that's your 2x, and your last terms, that's minus 2. So you get a lot of monomials, and then you combine where you can. But what's the philosophy? There's a more general philosophy. FOIL works well when I have something plus something times something plus something. Then FOIL works. What if I have bigger things? Then I don't want to have to come up with a longer acronym, but I want to understand a basic principle. So here's the rule of thumb. We're going to combine one term from the first piece with one term from the second piece in every possible combination. So we're going to multiply all pairs of monomials where we take one from the first and one from the second. And so we're going to build up a big collection of monomials. And then we add them up. And if you think about what FOIL is, here I have two monomials to pick from. And here I have two monomials to pick from. So there's two I can pick from the first, two I can pick from the second. So that gives me a total of 4 combinations, 2 times 2. So when I multiply out, I have 4 pieces, and I put them back together. And here's a suggestion, a tip. Good bookkeeping helps make the job easier and leads to fewer mistakes. Also, being systematic. Just don't randomly do things. Do things in some logical order. All right. Well, let's try this out. So, multiply the following. 4x minus 1 times 2x squared minus 3x minus 5. It's a little bit more challenging than foiling because there's 3 pieces here. Now, as an intermediate sort of thought along the way, we're going to multiply this down, make a big collection of monomials first. How many different monomials will we have initially after we do our multiplication? I heard 6. Where does 6 come from? I have 2 things I can pick for my monomial here. 3 I can pick there. 2 times 3 is 6. So let's do this. And I like to be systematic. And okay, so what do we have? 4x, I'm just going to start with the first term and just consistently go through. 4x times 2x squared gives 8x cubed. 4x times minus 3x. Don't forget the minuses. Pay attention. Gives negative 12x squared. 4x times minus 5. Minus 20x. Okay, so I multiplied the first term through. Now I'm going to do the second term through, and sort of to help me follow what's going along, I could write it next to it, but I can also write underneath it. And if I write underneath, I can combine powers. That might help me with simplifying. So now I'm with the minus 1. Minus 1 times 2x squared. Negative 2x squared. And I'm going to put that right underneath my other x squared term. Minus 1 times minus 3x. What is it? Positive 3x, right? 2 wrongs make a right. No. Minus times a minus makes a plus. Minus 1 times minus 5. Plus 5. All right, so there's my 6 terms. And we're going to add these up. And what do we get? 8x cubed. That's the only cube. What about the x squareds? What do we get? Minus 14x squared. For x's, minus 17x. For the constants, plus 5. And there we go. That's the idea. All right. Well, how about this next one? A plus B quantity cubed. Now, what does A plus B quantity cubed mean? So A plus B cubed means there's 3 copies of A plus B. So A plus B, A plus B, A plus B. 3 of them. And you might be thinking, wait, we only talked about how to multiply 2 things together, and here you're asking to do 3 things. Well, that's okay. Because what can we do? Well, one thing we can do is just say, hey, let's just multiply these 2 parts together, and we'll leave this out in the front. So we'll have an A plus B in the front that we haven't worked with. And now, let's take A plus B times A plus B. Does anyone know that? Or we can do our FOIL. Somebody has taken algebra before. A squared. Actually, I think most people have taken algebra before. A squared. Then you have an AB and an AB. That's a 2AB. And then you have a B times B. That's a B squared. Okay, now what can we do? Well, now we can multiply these 2 together. Same philosophy, so it's not going to be too different. They'll feel familiar. A goes through each term, so that's an A cubed, a 2A squared B, and an AB squared. And then we'll put a B through each term. So, okay, so then we have a B times A squared. Well, that looks a lot like that, so I'll put that underneath here, A squared B. Then we'll have a B times 2AB. That'll give 2ABB. Oh, that's probably 2AB squared. I think that's how they say it these days. And a B times B squared is B cubed. Add them up. A cubed, 3A squared B, 3AB squared, and B cubed. All right. Now, any questions? All right. I think you'll have a lot of problems on the homework of this kind of flavor. So you'll get plenty of practice. Someone did recognize the square. There are some common products that you'll see frequently. So if I have x minus a, x plus a, this is x squared minus a squared. If I see x plus a quantity squared, that's x squared plus 2ax plus a squared. If I see x minus a squared, that's x squared minus 2ax plus a squared. So we have the difference of squares, and we have the perfect squares. And these are both things which are very useful to know. Perfect squares are very nice because there's reasons for us to want perfect squares, because that makes it easy to factor. And it's one of our underlying ideas. Difference of squares shows up a lot. Almost, we kind of rigged the game, I think, when it comes to difference of squares. But that's okay. That's all right. And, all right. Let's see, what else to say? Okay. Well, there's some advice here. When simplifying expressions, work through one layer at a time. I recommend going from inside to out. I like to say this, that oftentimes when simplifying expressions, these are what I might call onion problems. Because onions have layers. And there might also be some tears involved along the way. But it's just a matter of being methodical and working through it. Oftentimes, Big problems look scary because you're looking at it all at once. But big problems are almost always a series of small problems that you do along the way. So don't get overwhelmed by a big expression. Just start chipping away, bit by bit, cleaning up, making it look simpler until eventually you get what you need. Now, there's some advice. You should work according to order of operations. Order of operations is just a way of saying we want to make sure we get consistency. So I like to say, work with what's inside of parentheses first. So simplify what's inside parentheses. Once you've done that, handle any powers that you need to. After you've done that, handle any multiplication you need to, and then add. Now, I don't want to imply that it's always going to be as simple as you do this, then you do this, then you do this. You might end up cycling through this several times depending upon how many layers you have. And again, don't stress too much about big problems. Big problems are just small problems in disguise. All right, I think we have enough time left to do this problem. Find 5a minus 2b minus 2b plus 5a minus 2b quantity squared minus 2b plus 5a, that quantity squared. There's two ways to approach this. Let's see if we get the same answer in both ways. What do you want to try? Well, how about let's expand and take the difference. Because 5a minus 2b quantity squared, what is that? It's a square, right? It's something squared. So if we follow the rules for squaring, the rule says you square the first term. So what's the square of the first term? 25a squared. And because there's a minus here, then it's minus 2, the first term, times the second term. So this is your first term squared minus 2, first term, second term. And what else do we need?
Plus 4b squared.
Plus the last term squared, 4b squared. So we could have written this 25a squared as 5a quantity squared, this 4b squared as 2b quantity squared. So we're using difference here, and we're taking a square of a difference. Okay, now that's the first term. We'll clean that up in a second. What about this second term? Now it's a sum, a square of a sum. So what do we have? Okay, so we have the square of the first term, 4b squared. And then? Plus, sum plus 2 times the first times the second. And then 25a squared. Okay. Well, let's clean this up. So this becomes 25a squared. We're going to work on dropping parentheses. Minus 2 times 5a times 2b. What's another way to write that? Minus 20ab. The 4b squared looks a lot like 4b squared. Okay, for the second term, when we drop the parentheses, what do we need to do? Because after all, we want all our points. Got to get them all. Yeah, don't forget this minus. It's going to come through. So what do we have? Minus 4b squared. Minus 2 times 2b times 5a becomes minus 20ab, and then minus 25a squared. Okay, does anything simplify? The 25a squareds, the 4b squareds. So what do we end up with? Negative 40ab. All right, we're almost out of time. So in the interest of time, we used the perfect squares to expand. But what else do you see here? It's blah squared, blah squared. So what else do you have? This is also a difference of squares. So we could have gone backwards and said, this is 5a minus 2b, subtract 2b plus 5a, times 5a minus 2b plus 2b plus 5a. And if we do that, the 2b's cancel here, the 5a's cancel here, so you get minus 4b times 10a, which is minus 40ab. So you will always get the same answer because math is consistent. If you didn't, mistakes were made. That's it for today. We'll pick up again next time.